Hello everyone, welcome back to Technologies Discussion channel. Today, I'd like to continue the discussion on the different modes of radio wave propagation. In short, there are actually three modes of radio wave propagation. The first one will be ground wave propagation, followed by sky wave propagation. This video, I will concentrate on space wave propagation. Okay, so under this space wave propagation, we have both the direct wave or the ground reflected wave, which I will further explain later on. Guys, if you're keen to know more about radio wave propagation, okay, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on radio wave propagation. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you prefer to have a faster response, I actually urge you to comment, okay, rather than sending me an email. Before I continue, okay, I'd like to urge you guys to help me by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Okay, let's quickly understand the space wave propagation, okay, so which is also one of the mode of radio wave propagation. In this case here, the electromagnetic wave actually travel directly from the transmitting antenna to the receiving antenna, okay, with the line of sight. Okay, so basically take a look on this blue color line. So this is what we call the direct line of sight wave. So basically this is actually classified as space wave propagation. Okay, beside direct line of sight, okay, we actually also have this after they actually reflected off the Earth's surface, okay, or troposphere. Okay, so this is actually also classified as the space wave, okay, which is known as the ground reflected wave. So in short, for example, under this case here, if we receive the direct line of sight and also the ground reflected wave, okay, although this ground reflected wave may cause some issue, okay, when we actually receive the antenna, because there will be some phase difference. However, this still classified under this space wave propagation. Or if not, if we're going to have just the direct line of sight, we also consider them as space wave propagation. This brings to another question. Okay, does this satellite communication communicate to, let's say, this ground station? Does this consider space wave propagation? The answer is yes, because I mentioned earlier on, either just the single direct wave, okay, or the direct wave together with the ground reflected wave, we consider them as space wave. Okay, so let's continue. Okay, so a direct wave or space wave, they travels in a straight line from the transmitting antenna to the receiving antenna. Okay, so basically this is what I mentioned earlier on. Or from this diagram here, you can see that this is basically line of sight, which means that the transmitter antenna and the receiver antenna, they can look at each other. Okay, nothing block them. So this is what we call the direct wave. Okay, so this type of radio signaling is often called line of sight communication. Under this direct wave, okay, so there should not be any reflection. Okay, neither they should follow the Earth curvature, okay, which means that they're not supposed to bend. Okay, so basically when they bend, okay, basically this will not fall under the space wave propagation. Okay, but they also should not be blocked or reflected by any obstacle, and they cannot travel beyond the horizon or behind obstruction, which means that let's say there's a building here which block the line of sight, then we cannot classify them as space wave propagation. If not this horizon, just imagine the receiving antenna is much shorter, which is over here. Then again, we cannot classify this as under this space wave propagation. Next, let's come to the characteristics of space wave propagation. Firstly, the frequency range. Okay, so most of the time they typically use for VHF, okay, which is from 30 megahertz to 300 megahertz. Okay, so this frequency mainly will be for this direct line of sight. Okay, so this will be for the direct line of sight, mainly for this frequency range. While for the UHF, okay, which is higher frequency from 300 megahertz to 3 gigahertz, you can imagine that probably they are mainly for this form of communication, okay, all the way to satellite or even radar communication here. So this is actually called the higher frequency, ultra high frequency. So this space wave propagation is commonly employed in TV broadcasts, FM radio, mobile communication, and also radar system. Okay, so basically these are where the application of space wave propagation. Next, on the line of sight, okay, they actually depend highly on this line of sight. Okay, so since space wave travel in a straight line, the transmitting and receiving antenna must be within each other vision horizon. Okay, which means that they will be able to look at each other. For example, if we have obstacle like building or mountain, okay, basically all these can block the signal, and hence we can't classify them as space wave propagation anymore. Third, okay, so basically we are actually limited by the Earth curvature. As you can see from here, imagine the antenna is slightly shorter, then the Earth probably will disturb the line of sight. So this is what it means. So the maximum distance for line of sight communication is actually determined by the height of the antenna. Okay, so this is actually the formula to calculate the line of sight. Maximum so-called distance, okay, for the line of sight to so-called to happen. So basically the distance here, okay, will be this distance here. So from this equation here, you can see that it's actually a function of the height of the transmitting antenna and also the receiving antenna. Okay, one thing I want to highlight, this is, I would say that this way of calculate the distance mainly for the theory form. Okay, so later on I will prove more practical. Okay, so basically this is the theory form of proving the maximum line of sight distance. Okay, but like I mentioned earlier on, later on, I will actually prove with the radio horizon. Okay, so that will be more real life application. But over here, you can see that the distance here already, okay, so this distance here will be in meter. The height and also the receiver antenna will be in meter also. Next, okay, the fourth one, okay, which is tropospheric effect. Okay, space waves can be slightly reflected due to changes in the tropospheric refractive index. Okay, there are different refractive index, and therefore they probably will be reflected. Sometimes, okay, tropospheric ducting can extend the range beyond the line of sight under certain atmosphere condition. Next, multipath propagation. Okay, the signal may reach the receiver via multipath, like I mentioned earlier on, which is the direct plus the reflected wave. This actually creates some so-called phase difference, okay, which means that they actually cause some fading or interference, which may not be desired. Coming to the advantages of and also the disadvantages of space wave propagation. Okay, so for space wave propagation, it is actually suitable for high frequency communication. Okay, for the very high frequency and ultra high frequency range. They actually provide very stable and high quality signal within the line of sight range. Okay, which means that as long as you guarantee line of sight, okay, they actually provide a very stable and high quality signal. They are actually less affected by atmospheric layers compared to skywave propagation. Okay, so basically these are under the advantages of space wave propagation. As for disadvantage, okay, we have limited range, okay, because of the Earth curvature, because the Earth is not flat. Okay, there will be some curve on the Earth, and because of that, we have some limited range. It require, okay, tall antenna in order to establish long distance communication. It's also very sensitive to obstacle and terrain blocking. Okay, so basically this highlight the advantages and also the disadvantages of space wave propagation. Before I continue, guys, this is very important for me. Okay, I urge you to help me, okay, by like this video. Give me a few seconds. Help me to press the like button now. If you have learned something from this video, or maybe later on, if you feel that you learned something from this video, help me and support me by subscribing to this channel and turn on your notification bell. Once again, thank you so much. Let's come to the equation. Okay, so as I explained earlier on, this is to calculate the maximum distance, okay, between the transmitter and the receiver. Okay, so this equation calculation is much more so-called real life, okay, because they actually take care of the radio horizon, okay, which is more appropriate for a real life calculation. But let me quickly go through this discussion here. Okay, so we are going to, this is earlier on, which I told you that this is a very practical sense of formula. Okay, but have decided to work another way so that it will be more real life calculation here. Okay, so basically the distance D as you can see that it will be a summation of D1 over D2, which I quickly written over here. So I just like to concentrate on D1. Okay, imagine this is actually like a triangle, okay, with a 90-degree here. Okay, so basically this is actually a triangle. So from here you can see that this is actually D1. This is actually the radius of the Earth. This is the radius of the Earth, including the height of the transmitting antenna. And in order to find my this D1, it will be the length of this thing here, including the height of the transmitting antenna, okay, squared, okay, and then minus away this R squared, which I have written here. So this R plus HT, which is the length of the radius of the height of the Earth plus the transmitting antenna height. So this is the term here. This minus R squared here. This will give me the D1 distance from this here. So next what I'm going to do is I open up the bracket. So basically it become R squared plus 2RHT plus HT squared here. Okay, this is nothing, just mathematical. I just open out this bracket. From here, I can see that minus R and R, I just cancel them each other. And I finally arrive at this equation. Okay, one assumption that I want to take for this equation to arrive on this part here, basically I just want to concentrate on this. Okay, so when the height of the transmitting antenna as compared to the radius of the Earth, okay, I would say that this number is significant bigger than the height of the transmitter antenna. Okay, so basically, therefore, I can actually omit this term. Okay, it makes sense, right? Because the radius of the Earth definitely will be much bigger as compared to the height of the transmit antenna. So therefore, I omit this term. And therefore, from here, you can see that my D1 is actually equals to 2RHT. Next, since this is how I find my D1, okay, the D2 will be similar, okay, because they also form a so-called a triangular, okay, with a right angle here. So from here, you can calculate that this will be the formula to calculate the D2. Like I mentioned earlier on, this distance is actually equals to D1 plus D2. Okay, so basically this D1 is actually from here. D2 are just coming down from here. I just take the common factor, okay, which is the square root 2R, and this is actually what is left over. So we know that the radius of the Earth will be equal to 6370 kilometer. And if I do this square root 2R, I will arrive at this number. And basically from this equation here, this equation derives the maximum possible distance, okay, with the given height of the transmitting antenna and also the receiving antenna. Okay, so basically in short, this is what I have for the space wave propagation. Okay, with this, I'd like to end my discussion. Please help to like this video and subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.